Bismillah ar-Rahman ar-Rahim. We have a continuous function f of x over compact set big X, which for convenience we can take to be the closed bounded interval from a to b. We are interested in constructing an approximation of the function f of x. This approximation is a sum with n terms. The ith term is the coefficient ai times gi of x. The functions g1 of x, g2 of x to gn of x are known. They are continuous functions on big X. We want to obtain the coefficients such that the L infinity norm of the error or the residual, the difference between the approximation and the function f of x, we need this L infinity norm to be minimized. We define the residual r of x to be the approximation summation I from 1 to n ai gi of x minus f of x. The L infinity norm of the error is the maximum of the magnitude of r of x, where small x is in big X. Our compact set, which again can be taken to be the closed interval from a to b. We obtain the coefficients such that this maximum is minimized. Before we proceed, let's go back to the g functions. They are continuous. They also need to satisfy the Haar condition. Take n points in set x that are strictly increasing. We have z1 less than z2 less than z3 less than zn. At each point, we can construct an n-dimensional vector. Generally, if we have a point z in the set big X, we can have this vector g out of z. We evaluate the function g1 at z. This will be the first component in the vector. We evaluate the function g2 at z, and we proceed till we evaluate the function gn of z. That's an n by 1 vector. If we have n points, we can construct n of those n by 1 vectors, and those n by 1 vectors are an n by n matrix. The first column in this matrix is obtained via evaluating the n g functions at the point z1. The second column in the matrix is obtained by evaluating the g functions at the point z2, which is strictly greater than z1, and so on. The Haar condition means that for any choice of those n points in set big X, the n by n matrix that we obtain is invertible, which means that the determinant of the matrix is not equal to 0. Again, the Haar condition means that if we choose n points in set X in a strictly increasing order, for any n points, we construct this n by n matrix. It must be invertible. The columns are linearly independent, and the determinant is not equal to 0. Here is an interesting implication of the Haar condition. For every n tuple of distinct numbers in ascending order, the determinant has the same sign. Suppose that we have those numbers and the determinant is strictly negative. If I take y1 less than y2 less than y3 less than yn, and all those guys are in the set big X, if the g functions obey the Haar condition, then if we construct the matrix with columns that look like this, the matrix is invertible and the determinant is non-zero. But we can say more. The determinant is negative. If the determinant is negative when we use z1, z2 to zn, it must also be negative if we use the numbers y1, y2 to yn. Let's do a proof by contradiction. Suppose that the determinant when we use the z's is strictly negative, but if we use the y's, the determinant is strictly positive. Consider theta in the closed interval from 0 to 1. Let's construct the following n by n matrix. The first column will be the g functions evaluated at theta z1 plus 1 minus theta y1. That's a convex combination of z1 and y1. The second column will be the g functions evaluated at the convex combination of z2 and y2, specifically at theta z2 plus 1 minus theta y2, and so forth. Note that if we want to compute the determinant of this matrix, the determinant will be sum of products of those g functions. The g functions are continuous. A product of the g functions will be continuous, and the sum of products will be continuous. The argument of each g function is an affine function of theta, which is continuous. The idea is that this determinant is a continuous function of theta. To be concrete, let's take the case of n equal to 2. This matrix here will be a 2 by 2 matrix. The first column will be g1 evaluated as theta z1 plus 1 minus theta y1. Element 2, 1 will be g2 evaluated at the same point theta z1 plus 1 minus theta y1. The second column is g1 evaluated at theta z2 plus 1 minus theta y2. Finally, element 2 is the function g2 evaluated at the same point here, theta z2 plus 1 minus theta y2. What is the determinant of this matrix? It is the product of these two, g1 theta z1 plus 1 minus theta y1 times g2 theta z2 plus 1 minus theta y2 minus g1 theta z2 plus 1 minus theta y2 g2 theta z1 plus 1 minus theta y1. Because the g functions are continuous functions and their arguments are affine functions of theta, then the determinant, whether when small n is 2 or any other positive integer, is a continuous function of theta. This continuous function of theta is strictly negative when theta is equal to 1, because when theta is equal to 1, this becomes z1, this becomes z2, and so forth. If theta is equal to 1, then this determinant is exactly equal to this one, assumed to be strictly negative. If theta is 0, then this determinant is exactly that determinant, assumed to be strictly positive. Because the determinant is a continuous function of theta, there must be a point strictly between 0 and 1. Let's call it theta tilde, such that the determinant, when we use theta tilde, is exactly equal to 0. The determinant is equal to 0 when we use theta tilde. We are assuming that our functions obey the Haar condition. So what is the implication? How can the determinant be equal to 0? Recall that the Haar condition tells us that if we choose distinct points in the set big X in this ascending order, then the determinant should be non-zero. The matrix should be non-singular. Now, when theta is equal to theta tilde, this determinant is equal to 0. And the g functions obey the Haar condition. The conclusion is that there exist distinct I and j in the set 1, 2, 3, all the way to n, such that theta tilde zi plus 1 minus theta tilde yi is equal to theta tilde zj plus 1 minus theta tilde yj. The g functions obey the Haar condition. So we cannot get the determinant equal to 0 unless there are 2 points that are exactly equal. If the points are distinct, then the determinant is not equal to 0. The determinant is 0 implies that 2 of those points are exactly equal. But this is nonsense. We can write down this equality as theta tilde zi minus zj equal to 1 minus theta tilde yj minus yi. Theta tilde is strictly positive. 1 minus theta tilde is strictly positive. Suppose that zi minus zj is strictly positive. So we have zj here and then zi. But then we have yj here and here we have yi, indicating that yj minus yi is negative. We have a strictly positive number equal to a strictly negative number. This does not make sense. And if we make zi minus zj negative, then this guy will be positive, and again we reach the same contradiction. What is false is our assumption that for some n distinct points, the determinant is negative, while for another set, the determinant is strictly positive. The determinant must have the same sign. It is not equal to 0 by how we define the Haar condition. But the new thing now is that evaluating the determinant for any set of distinct points in ascending order will give us the same sign. We will later make use of this property. The coefficients here used to construct the approximation for the continuous function f of x are obtained via minimizing the L infinity norm of the error or residual r of x. The L infinity norm is the maximum of this magnitude with a small x in the closed interval from a to b, or generally in the compact set big X. Let the L infinity norm be equal to gamma. Let's define the set big X 0. This is the set of small x values in big X at which the magnitude of the residual is equal to the maximum value gamma. So x0 will be the set of points in big X such that the magnitude of the residual is exactly equal to gamma. The residual function is a continuous function of x. The g's are continuous and f is a continuous function. And here we have the magnitude of a continuous function, which is a continuous function. Set x0 is non-empty by the extreme value theorem. The set of points small x at which this continuous function is equal to a particular value gamma is a closed and bounded set. This is a compact set. Note that if there is a point small x at which the magnitude is strictly greater than gamma, because of the continuity of this function, then there is a neighborhood of this point at which the magnitude is also strictly greater than gamma. The same if we take the magnitude strictly less than gamma. This means that the complement of this set, because of the continuity of this function, is an open set, and hence the set big X0 is a closed set. The fact that it is bounded is because the set big X itself is bounded. It is important to keep in mind that the set big X0 is a compact set. Here is how we characterize the optimality of the coefficients. The coefficients are optimal in the sense of minimizing the L infinity norm if and only if the all zero vector in the n-dimensional space is in the convex hull of a set of vectors that look like this. The set of vectors are n-dimensional. Here is an n-dimensional vector. We take small x in this set big X0, which means by definition that the magnitude of small r of x is equal to gamma. We have this n-dimensional vector where we evaluate the g functions at this x from the set x0. This is g1 of x, g2 of x, all the way to gn of x. We take this n-dimensional vector multiplied by the scalar, so we still get an n-dimensional vector, and the scalar is r of x. R of x has a magnitude equal to gamma because the small x is in big X sub 0, and r of x itself as an expression, it is summation I from 1 to n, ai gi of x minus f of x. The a coefficients are living in this r of x. They are right here. The coefficients are optimal if and only if we can take the all zero vector in n dimensions and write it as a convex combination of those vectors. So there are theta k's, those are non-negative and their sum is equal to 1. And we can write down the all zero vector as this convex combination of vectors that look like this, where xk is in the set big X0. If the all zero vector can be written as this convex combination, then the coefficients are optimal. And if the coefficients are optimal, then we can take the all zero vector and write it down as a convex combination of those vectors. In the first part of the proof, we assume that the coefficients are not optimal. We show that this implies that the all zero vector is not in the convex hull. It cannot be written as a convex combination of those vectors that we mentioned on the previous slide. The contrapositive is that if the all zero vector is in the convex hull, then those coefficients are optimal. How can we prove this? If the coefficients are not optimal, this means that there are n numbers, b1, b2 to bn, such that if we perturb the a coefficients by those n numbers, we can achieve a strictly lower L infinity norm for the residual. Now our approximation will be summation I from 1 to n, not ai times gi of x, but ai minus bi times gi of x. That's our new approximation. And the new residual is this summation minus f of x. The coefficients are not optimal. It means that we can perturb the a coefficients. We can use the new coefficients that have the form ai minus pi, and we can achieve an L infinity norm that is strictly less than gamma. Note that this L infinity norm can be written as the L infinity norm of the sum I from 1 to n, ai gi of x minus f of x. And this is the residual using the a coefficients minus summation I from 1 to n, bi gi of x. By assumption, this summation here cannot be equal to 0, because if this summation is equal to 0, what we have inside the L infinity norm is r of x using the a coefficients, and the L infinity norm using the a coefficients is equal to gamma. To say that we have now this function and its L infinity norm is strictly less than gamma means that this summation here cannot be equal to 0. By the definition of an L infinity norm, the magnitude of this summation minus f of x is less than or equal to the L infinity norm, which is assumed to be strictly less than gamma. In this magnitude, let's use a small x that is in the set big X of 0. Square summation ai gi of x minus f of x, that's the residual with the a coefficients. And when we square, we will get rx squared. And then we will get the square of this summation here, summation I from 1 to n, bi gi of x. And then we have a cross term minus 2 r of x, summation I from 1 to n, bi gi of x. This magnitude squared is strictly less than gamma squared. Note that we are not computing this left-hand side at an arbitrary small x. Small x is in the set big X0. Elements small x in this set satisfy that the magnitude of r of x is equal to gamma. This quantity here is equal to gamma squared. We can eliminate gamma squared on both sides. And what we have is that r of x, summation I from 1 to n, bi gi of x, is strictly greater than 1/2 summation I from 1 to n bi gi of x all squared. Note that this summation cannot be equal to 0. This square is strictly positive. What we have is that summation I from 1 to n bi r of x gi of x, this is a strictly positive quantity for any small x in the set big X 0. If we collect the b's in an n-dimensional vector with components b1, b2 to bn, I can write down this summation as an inner product between vector b and n-dimensional vectors that look like this, rx g arrow of x. Recall that this vector is the scalar r of x multiplied by the n-dimensional vector in which we evaluate the g functions at x, g1 of x, g2 of x, all the way to gn of x. We have for every small x in big X 0, this inner product is strictly positive. What does this mean? Suppose that you have vector w in the convex hull of those vectors. Vector w is equal to summation small k from 1 to big K, theta k, and then those vectors are xk, g arrow of xk. This is a convex combination because we are saying that w is in the convex hull of those vectors. A convex combination is a linear combination in which those coefficients are greater than or equal to 0, but their sum must be equal to 1. And if the sum is equal to 1, it means that at least one of those coefficients is strictly positive. If B transpose times this vector is strictly greater than 0, then B transpose times theta k, which is this non-negative coefficient, Rx of k, g arrow of x of k. This is strictly positive, and it's 0 if theta k is equal to 0. But B transpose times W, which is B transpose times the sum small k from 1 to big K, theta k, r of xk, g arrow of xk, this is strictly positive. And the reason for this is that at least one of the thetas is strictly positive, and the inner product of B and any of those vectors is strictly positive. The conclusion is that B transpose times any vector in the convex hull of the vectors Rx, g arrow of x, and x is in the set big X0, this is strictly positive. The all zero vector in the n-dimensional space cannot be in the convex hull. If the all zero vector is in the convex hull of those vectors, then B transpose times the all zero vector will give us 0. But P transpose times any vector in the convex hull is strictly positive. Therefore, the all zero vector of the n-dimensional space is not in the convex hull of those vectors. What we have proved is that if the coefficients are not optimal, they do not minimize the L infinity norm. We can perturb those coefficients by the BIs and obtain a lower L infinity norm than gamma. The conclusion is that the all zero vector is not in the convex hull. This is equivalent to the following statement. If the all zero vector is in the convex hull, if the all zero vector can be written as a convex combination of those vectors, then the set of coefficients is indeed optimal in the sense of minimizing the L infinity norm. The next step is to show that if the all zero vector is not in the convex hull of those vectors, then the coefficients are not optimal. The contrapositive is that if the coefficients are optimal, then the all zero vector must be in the convex hull. To prove this, we will use a result from convex analysis. If there is a set S, a subset of the n-dimensional space, set S is non-empty, closed, and convex. There is a point V that is not in the set. There exists a vector lambda such that lambda transpose times any vector in this set Z is strictly greater than lambda transpose V, which is this vector outside the set. Our set here is non-empty because x0 is non-empty. Recall that x0 is the set of points small x in big X such that the magnitude of the residual is equal to the L infinity norm gamma. This is a continuous function, and a continuous function over a compact set achieves its maximum. The convex hull is closed because the continuous image of a compact set is compact. Also, the convex hull of a compact set in the n-dimensional space is compact. From the definition of convexity, we can show that the convex hull is indeed a convex set. In our case, vector V is the all zero vector because our starting point is that the all zero vector is not in the convex hull. There exists lambda, a vector in Rn such that the inner product between lambda and any of those vectors, so lambda transpose Rx G arrow of x, and x of course is in the set big X 0. This is strictly greater than the inner product between lambda and the all 0 vector, that's 0. For every small x in x0, lambda transpose Rx G arrow of x is strictly positive. Let's take the minimum of this function over small x in x0. Because this is a continuous function and this is a compact set, the minimum is achievable. Let's call it epsilon. Epsilon is strictly positive. Now let's define a new set, big X1. This is the set of small x in big X, our original compact set, such that this function here, lambda transpose Rx G arrow of x, is less than or equal to epsilon divided by 2. All the points small x satisfying this inequality will be in the set big X sub 1. If there is a point small x in big X, but small x is not in x1, then we know that for this small x, lambda transpose Rx G arrow of x is strictly greater than epsilon over 2. If we multiply both sides by -2, then -2 lambda transpose Rx G of x is strictly less than minus epsilon. We can use this inequality for later bounding if small x is not in the set big X sub 1. This set, by the way it is defined, and since this function is continuous, is also a compact set. Let E be the maximum of the magnitude of the residual. Here we are doing the maximization only using the elements of x1. The question is, can E be equal to gamma, or is E strictly less than gamma? Let's think about this. Can E be equal to gamma? Suppose that this is the case. Then there is an x bar, which is in the set x1. The magnitude of Rx bar is equal to gamma. If x bar satisfies this equality, then x bar must be in the set x0, which by definition contains all small x in big X, at which the magnitude of the residual is equal to gamma. If we assume this, x bar is in x1 and is in x0. But this cannot be the case. Why? Because for every x that is in x0, we have this quantity, lambda transpose Rx G arrow of x, is greater than or equal to epsilon. Recall that epsilon is the minimum of this quantity with a small x in x0. For small x in x0, this quantity is epsilon or more. But we defined the set x1 such that this quantity is epsilon over 2 or less. By the way, we have defined epsilon and x1. There can never be an intersection between the set x1 and the set x0. Their intersection is empty. If we assume that E is equal to gamma, we will get a non-empty intersection. This is a contradiction. E must be strictly less than gamma. Our starting point has been that the all 0 vector is not in the convex hull. Our goal is to show that the A coefficients are not optimal. We need to show that we can perturb those coefficients and obtain an L infinity norm that is strictly less than gamma. Our goal, show that for every small x in big X, the magnitude of the residual with those modified coefficients, ai minus eta, which is a strictly positive real number, times lambda I, and lambda I is the ith component in this vector lambda. So if we use those as our coefficients, and thus this summation now is our approximation, the magnitude of the residual will be strictly less than gamma. If we show this, this means that perturbing the E coefficients allows us to achieve a smaller L infinity norm, thereby indicating that the A coefficients are not optimal, and this is our goal. Let's start by taking small x in x1. Let's compute this magnitude, which can be written as the magnitude of the residual using the A coefficients minus eta summation I from 1 to n lambda I g I x, and this term here is exactly equal to eta lambda transpose g arrow of x. Let's apply the triangle inequality. This magnitude is less than or equal to the magnitude of r of x plus the magnitude of this term here. Eta is strictly positive, so we put it here, and then we have the magnitude of lambda transpose g arrow of x. This magnitude is computed for small x in x1. We can upper bound this by the L infinity norm of lambda transpose GR of X computed for every X in big X. Because we are using small x values in the set X1, those magnitudes are upper bounded by E, which we have shown to be strictly less than gamma. So this magnitude is less than or equal to E plus eta, and then the L infinity norm of lambda transpose GR of X. Can we choose eta such that this upper bound is strictly less than gamma? Yes, if we choose eta, which is positive, to be less than gamma minus E divided by the L infinity norm. For any eta obeying this condition, we are able to make this magnitude of the modified residual strictly less than gamma, which is the L infinity norm of the residual if we use the coefficients A1, A2 to AN. Are we done? Not yet, because the goal is to investigate every small x in big X. We have studied small x in X1. Our next step is to take small x not in X1. Let's investigate the magnitude squared. Here we have the square of the residual, and this is upper bounded by gamma squared. We have eta squared, and then the square of this quantity. We have minus 2 eta lambda transpose R of X GR of X. This term here is upper bounded by eta squared, the L infinity norm squared of lambda transpose GR of X. So this is upper bounded by gamma squared, eta squared, the L infinity norm squared, and then we have this term here. We have defined the set X1 such that lambda transpose Rx GR of X is less than or equal to epsilon over 2. If a small x is not in X1, we replace this by greater than. If we multiply by minus 2, then we have minus 2 lambda transpose Rx GR of X strictly less than minus epsilon. Eta is positive, we can multiply both sides by eta. This term here can be upper bounded by minus eta epsilon. I can write these three terms as gamma squared plus eta, and then inside the bracket we have eta times the L infinity norm squared minus epsilon. Can we make this strictly less than gamma squared? Yes, if we can make the bracket strictly negative. Can we make the bracket strictly negative? Yes, because we can choose eta to be strictly less than epsilon over the L infinity norm squared. We can now combine the two cases. Small x is in X1, small x is not in X1. This covers small x in big X. If we choose eta to be positive and strictly less than the minimum of these two quantities, then we are able to make the magnitude of this quantity, which again can be thought of as the residual. If we use the coefficients in the form of ai minus eta lambda I, we are able to make this magnitude for every small x in big X strictly less than gamma. The a coefficients are definitely not optimal. Note that the lambdas cannot all be equal to 0, because we have that lambda transpose Rx GR of X is strictly positive. If the lambda vector is the all 0 vector, this inequality cannot be true. So by the theorem that we have used from convex analysis, it is automatic that the lambda vector is not the all 0 vector. Those guys here are not all 0. We can perturb the a coefficients and achieve a lower L infinity norm for the residual, thereby demonstrating the non-optimality of the a coefficients, assuming that the all 0 vector is not in the convex hull. The contrapositive is that if the coefficients are optimal, then the all 0 vector is in the convex hull. It can be written down as a convex combination of those vectors. Let's recap our proof. We want to show that the a coefficients are not optimal, and we do this by investigating the magnitude of a modified residual. So this is the magnitude of R of X minus eta lambda transpose G bar of X. This is equal to the magnitude of summation I from 1 to n ai minus eta lambda I, the ith component of this vector lambda Gi of X. This is our new approximation using these coefficients minus f of x. We want to show that for every small x in big X, this magnitude is less than gamma. If we take this guy and square it, we get the magnitude squared of R of X plus eta squared lambda transpose GR of X squared minus 2 eta lambda transpose R of X GR of X. This is less than or equal to gamma squared, and this is less than or equal to the L infinity norm of lambda transpose G of X squared, here computed over all x in big X, and then we have this term here, minus 2 eta lambda transpose R of X GR of X. This is equal to gamma squared minus eta. We have 2 lambda transpose R of X GR of X minus eta, and then the L infinity norm squared. Can we make this less than gamma squared? Yes, we can do so if this is strictly positive. To make this strictly positive, consider an epsilon that is strictly positive. If eta is less than this positive epsilon divided by the L infinity norm squared. And if this epsilon here is strictly less than 2 lambda transpose R of x G R of x, then eta is less than 2 lambda transpose R of x G R of x divided by the L infinity norm squared. And if this is the case, then this bracket here is strictly positive, and this is strictly less than gamma squared. But if we want to do this bounding, we need this to be true. Are we guaranteed to have this inequality here for every small x in big X? Is it the case that for every small x in big X, we have that lambda transpose R of x G R of x is strictly greater than epsilon over 2? No, there is no guarantee. If this inequality is satisfied, we are good. But what if it is violated? This is the motivation behind the introduction of this set big X1. Let's define the set big X1 to be the set of small x's in big X such that lambda transpose Rx G R of x is less than or equal to epsilon over 2. For those small x's, we cannot use this bounding argument. For small x in big X1, we need a different upper bound. The idea is to take this epsilon, this positive epsilon, to be the minimum of small x in x0 of lambda transpose R of x G R of x. This minimum is achievable because this is a continuous function over a compact set. The meaning is that for every small x in big X0, we have lambda transpose R of x G R of x greater than or equal to epsilon. If this is the case, then the intersection between x0 and x1 is empty. For every small x here, this quantity is epsilon or more. For every small x there, this quantity is epsilon over 2 or less. The crucial thing is what is the maximum of the magnitude of the residual using the set x1. This is what we have called E. Can E be equal to gamma? If this is the case, it will disrupt our effort. The good news is that this must be strictly less than gamma. And the idea is here. If E is equal to gamma, then there is a point small x in big X1 that is also in big X0, which contains the points with a magnitude of the residual equal to gamma. But the intersection is empty. This maximum is strictly less than gamma. And because this maximum is strictly less than gamma, for those points that are in X1, for those points for which we cannot use this trick here, what we can do is we take the residual minus eta lambda transpose GR of x and upper bound using the triangle inequality, and the magnitude of this guy can be upper bounded by the L infinity norm. Now this is upper bounded by E plus eta and the L infinity norm. Now we can make this strictly less than gamma, because if we choose eta to be strictly less than gamma minus E divided by this L infinity norm, we are good. We have finished the proof of our characterization theorem. The coefficients from A1 to AN are optimal in the sense of minimizing the L infinity norm of the residual or the error if and only if the all zero vector of the n-dimensional space belongs to the convex hull of those vectors. The all zero vector is to be represented as a convex combination of vectors from this set here. Set of vectors R, X, G, R of X, where X is in X0. The question now is, how many terms do we need for representing the all zero vector as a convex combination of vectors from this set? To answer our question, we make use of Carathéodory's theorem. Consider vector Z, which is in the convex hull of those vectors. We write Z as a convex combination of those vectors. The coefficients of the convex combination are generally non-negative and their sum is equal to 1. But if there is a coefficient that is equal to 0, we can just eliminate the respective term in the summation. Let's focus on the case in which Z is a sum k from 1 to m, theta k, hk, so those are the vectors used to represent Z, and the thetas are all strictly positive. How many terms do we have in this convex combination? M. Suppose that those vectors are d-dimensional. We will assume that m is strictly greater than d plus 1. Let's construct the following set of vectors: h2 minus h1, h3 minus h1, all the way to hm minus h1. We take the vectors from here, starting from the second one, and from each vector, we subtract the first vector, which is h1. How many vectors do we have in this set? We have m minus 1 vectors. m is strictly greater than d plus 1, then m minus 1, by our assumption, is strictly greater than d. Those vectors are d-dimensional. We have m minus 1 of them, and m minus 1 is strictly greater than d. This implies that those vectors must be linearly dependent. And if they are linearly dependent, then there is a set of coefficients, alpha 2, alpha 3, all the way to alpha m, not all of them equal to 0, such that the linear combination alpha 2 times h2 minus h1 plus alpha 3 times h3 minus h1 all the way to alpha m times hm minus h1. This linear combination is equal to the all 0 vector. Again, the idea is that we start with m vectors where m is greater than d plus 1 and our vectors are d-dimensional. This set of vectors, h2 minus h1, h3 minus h1, and so forth, this set of vectors has m minus 1 vectors, and m minus 1 is greater than the dimensionality of each vector. So the vectors are linearly dependent, and we can write down the all 0 vector in the d-dimensional space as a linear combination of those vectors where the coefficients are not all equal to 0. There is at least one alpha coefficient that is non-zero. Define alpha 1 to be minus the sum k from 2 to m of alpha k. We can then move the sum to this side, join alpha 1 to the sum. We have summation k from 1 to m of alpha k is equal to 0. If we go back to this expression, it is summation k from 2 to m alpha k hk. Then we have minus the sum k from 2 to m alpha k. This sum is multiplied by the vector h1. This is equal to the all 0 vector in d dimensions. By definition, this summation is minus alpha 1. So this here is alpha 1 h1, which can be joined into the sum. We have a sum k from 1 to m alpha k hk, and this is equal to the all 0 vector. We can go back to our vector z. We can write down z as summation k from 1 to m. The vector hk is multiplied by theta k minus a positive real number eta alpha k. This is true because summation k from 1 to m theta k hk is z, and summation k from 1 to m alpha k hk is the all 0 vector. So this is another way for representing z in terms of the vectors from h1 to hm. Is this a convex combination? This is a convex combination if those coefficients are non-negative and if their sum is equal to 1. Till now, this is just a linear combination. What about the sum of those coefficients? Summation theta k minus eta alpha k. This is the summation k from 1 to m theta k, and this sum is 1 because we have started with a convex combination. Minus eta summation k from 1 to m alpha k, and this summation is indeed equal to 0. Those coefficients here have a sum of unity. This is a convex combination if each of those new coefficients is non-negative. Eta is chosen to be a positive real number. If alpha k is less than or equal to 0, then theta k minus eta alpha k is greater than or equal to theta k, and the thetas are strictly positive. So we have no problem if alpha k is 0 or if alpha k is negative. In this case, those coefficients are guaranteed to be positive. But what if alpha k is positive? There is at least one alpha k that is positive because the sum of the alpha k's, k from 1 to m, is equal to 0, and we are sure that at least one of the alphas is non-zero. We set eta to the following value. For every alpha k that is strictly positive, we compute theta k divided by alpha k. So we do this for every alpha k that is strictly positive. The minimum of those ratios will be our choice for the value of eta. If eta is given as such, then eta is less than or equal to theta k over alpha k. Alpha k is positive, we can multiply both sides by alpha k, and we get that theta k minus eta alpha k is greater than or equal to 0. This choice will make this true, and we get new coefficients. All of them are non-negative. But note that we choose eta to be exactly the minimum of theta k over alpha k. Suppose that the minimum occurs when k is equal to j. In this case, eta is equal to theta j over alpha j, and theta j minus eta alpha j is exactly equal to 0. We started with vector z written in this way. It's a convex combination of those h vectors. The theta k's are all strictly positive. We have m terms in the summation, and we assumed that m is strictly greater than d plus 1. Those vectors are d-dimensional. We rewrote z as this linear combination. For those coefficients, their sum is equal to 1. And if we choose eta in this way, the coefficients are non-negative and their sum to 1, then this is indeed a convex combination. But there is something else. One of those coefficients is guaranteed to be exactly equal to 0. And this 0 term can be removed from this summation. Rather than the sum having n terms, now it has m minus 1 terms or less. Starting from this convex combination, we can obtain another convex combination with a number of strictly positive coefficients that is less. What allowed us to do this is this assumption that m is greater than d plus 1. So we can keep reducing the number of terms in the summation till m is equal to d plus 1. This is our conclusion. The number of terms that we need in the convex combination is at most d plus 1 if our vectors are d-dimensional. If we have more, we can apply this procedure to reduce the number of terms. In our problem, the vectors are n-dimensional. The all-zero vector can be written as a convex combination of n plus 1 or less of the vectors from the set here. Suppose that the all-zero vector can be written as a convex combination with n terms. Let's even assume that some of those coefficients can be 0. Of course, not all of them, because their sum is equal to 1. The xj's here are from the set x0. Can we have something like this in our problem? Let's rewrite this summation here. I will have a column vector in which we have theta1 rx1, theta2 rx2, all the way to theta n rxn. That's an n by 1 vector. This summation here can be represented as this vector multiplied by a matrix from the left. The first column in the matrix is g arrow of x1, the second column is g arrow of x2, and so forth. This expression means that the matrix, the n by n matrix by the vector, will give us the all-zero vector of the n-dimensional space. We have chosen those x's to be in strictly ascending order. If the g functions satisfy the Haar condition, then this matrix is invertible. And if it is invertible, then the only vector in its null space is the all-zero vector. Every component here must be equal to 0. The residual function, because it is evaluated at points in this set, is either gamma or minus gamma. For this vector to be the all-zero vector, all the thetas must be equal to 0. But this is a contradiction because the thetas are non-negative and their sum must be equal to 1. For g functions that satisfy the Haar condition, we cannot have something like this. The all-zero vector in our problem must be represented as a convex combination of n plus 1 of vectors that look like this, where small x is in x0. The coefficients of the convex combination are all strictly positive. Let's examine our current situation. We have a continuous function f of x. We have an approximation for that function in this form, summation I from 1 to n, ai gi of x. The g's are continuous functions that satisfy the Haar condition. The difference between these is the residual. We will obtain the coefficients such that the L infinity norm of the residual is minimized. The coefficients are optimal in this sense if and only if the all-zero vector is in the convex hull of vectors that look like this: r of x, which is given by this expression, times an n-dimensional vector g arrow of x. We have those vectors for every x in the set big X0, which is the set containing the small x values such that the magnitude of r of x is equal to gamma, the L infinity norm. We have discovered that the all-zero vector needs to be written as a convex combination of n plus 1 of those vectors with coefficients here that are strictly positive. We can write down the all-zero vector using more terms, but it is enough to use n plus 1 terms in this convex combination. Let's take the x's to be in strictly ascending order. R of xk is either equal to plus gamma or minus gamma. Let's separate the term with k equal to 1, move this to the other side, and then divide by theta1 r of x1. Theta1 is strictly positive, r of x1 is either gamma or minus gamma. It is non-zero, so we can divide both sides by theta1 r x1. So we have this summation on the right-hand side. It has n terms, and on the left-hand side here, we have the vector minus g arrow of x1. Let's rewrite this as a matrix vector equation. We can collect those guys in an n by 1 column vector. the topmost element is theta 2 r of x2 divided by theta 1 r of x1. Then we have theta 3 r of x3 divided by theta 1 r of x1, all the way to theta n plus 1 r of xn plus 1 divided by theta 1 r of x1. And the matrix here will be gr of x2, gr of x3, all the way to gr of xn plus 1. Suppose that we want to solve for the components of this vector. Let's start by the topmost element, theta 2 r of x2 divided by theta 1 r of x1. We can obtain this first component by applying Cramer's rule. We can write down this first component as the ratio of two determinants. In the denominator, we have this matrix here, the determinant of the matrix with those columns from gr of x2 to gr of xn plus 1. In the numerator, we have the same matrix, but because we are interested in this first component, we will replace the first column by this vector here, minus gr of x1. We can take minus 1 outside the determinant, and now what we have is theta 2 r of x2 divided by theta 1 r of x1 minus, that's because of this minus sign here. In the numerator, we have the determinant of the matrix in which we have the g functions evaluated at x1, so this will be the first column, and then evaluated at x3, that's the second column, and x3 is strictly greater than x1, then x4, which is strictly greater than x3, and so on. In the denominator, we have the determinant of an n by n matrix. The first column is the g functions evaluated at x2. Then for the second column, we evaluated x3, which is strictly greater than x2, then x4, and so forth. Let's now recall one implication of the Haar condition. Remember that for the Haar condition, if we choose z1 less than z2 less than zn in the set big X, and then we compute the determinant of this n by n matrix, gr of z1, gr of z2, and so on, by the Haar condition, this determinant should be non-zero. But now, if we choose another n tuple, y1 less than y2 less than yn in the same set X, we get another determinant, and by the Haar condition, this other determinant must be non-zero. But we have done a proof by contradiction to show that these two determinants must have the same sign. Let's see our situation here. Upstairs, we have this determinant. Downstairs, we have that determinant. And these are the x's. These two determinants must have the same sign. Both of them are positive, or both of them are negative. In both cases, the ratio of these two determinants is strictly positive. But then there is a minus sign here. Therefore, theta 2 r of x2 over theta 1 r of x1 is negative. Theta 2 is strictly positive, theta 1 is strictly positive. This means that r of x2 and r of x1, they have different signs. R of x2 is equal to minus r of x1. If r of x1 is equal to gamma, r of x2 is equal to minus gamma. If r of x1 is equal to minus gamma, r of x2 is equal to gamma. Let's now try to get another component in this vector. Let's hunt for theta 3 r of x3 over theta 1 r of x1. That's the second component in this vector. By Cramer's rule, this is equal to the ratio of two determinants. The determinant downstairs is the determinant of this matrix here. In the numerator, we have the same determinant, but now the second column is replaced by the vector minus gr of x1. We can take minus 1 outside the determinant. The sequence of points in the n by n matrix in the numerator is x2, then x1, then x4, then x5, and so forth. Note that this is not in a strictly ascending order. x1 is less than x2. We can also interchange the first and second columns, and this will give us another minus sign. In other words, this determinant in the numerator is the Haar condition implies that the determinant in the numerator and the determinant in the denominator both have the same sign. Theta 3 r of x3 divided by theta 1 r of x1 is a positive number. Theta 3 is strictly positive, theta 1 is strictly positive. Therefore, r of x3 and r of x1 are both equal to gamma, or they are both equal to minus gamma. If we want to obtain the third component here, by Cramer's rule, it is the ratio of two determinants. In the denominator, we have this n by n matrix. In the numerator, we have the determinant of the n by n matrix obtained from this one here by replacing the third column by the vector minus gr of x1. The first column here is gr of x2. The second one is gr of x3. The third column is minus gr of x1. Then we have gr of x5, and so forth. we have -1 here that can be taken outside. To have the g functions in the matrix in the numerator evaluated at small x values in the set big X, such that the small x's are strictly increasing, we will need to swap this third column and this second column. If we do this, there will be a minus sign, and then we have a determinant. The first column is still g arrow of x2, the second column is g arrow of x1, and now the third column is g arrow of x3, and then g arrow of x5, and so forth. Here is x2, x1, and x1 is strictly less than x2. We need also to interchange the positions of these two columns. When we do this, we get another minus sign. So this is equal to the determinant of, we have an n by n matrix. The first column is g arrow of x1, then g arrow of x2, then g arrow of x3, then g arrow of x5, and so forth. x1, x2, x3, okay. The sequence here is strictly increasing. A very important implication of the Haar condition is that the determinant in the numerator and that in the denominator, they have the same sign. Their ratio is strictly positive. There is a minus sign here that came from that minus sign. Theta 4 r of x4 divided by theta 1 r of x1 is strictly negative. Theta 4 is strictly positive. Theta 1 is strictly positive. The residuals are either gamma or minus gamma. We can conclude that r of x4 is minus r of x1. R of x1 is either gamma or minus gamma. R of x2 is minus r of x1. R of x3 is equal to r of x1. R of x4 is equal to minus r of x1. We can continue doing this. The conclusion is that if we have in the set big X the points x1 less than x2 less than x3 and so on, r of xi plus 1 is equal to minus r of xi, where I is 1, 2, 3 all the way to n. This is the alternation theorem. There exist at least n plus 1 x values at which the maximum of the magnitude of the residual occurs with alternating signs. The residual r of x exhibits on the interval from a to b, or generally on the compact set big X, n plus 1 alternations. R of x sub I plus 1 is minus r of xi, and this is either plus gamma or minus gamma. Is our solution to the L infinity norm minimization unique? Suppose that in addition to the A coefficients, there are B coefficients that also minimize the L infinity norm of the residual. This means that this L infinity norm is gamma, and this other L infinity norm is gamma. Here we are using the A coefficients, here we are using the B coefficients. Let's examine an approximation for X using the coefficients that are AI plus BI over 2. The ith coefficient here is the arithmetic mean of AI and BI. Now, gamma is the minimum L infinity norm. So this L infinity norm using these coefficients is greater than or equal to gamma. Let's write this function as 1/2 summation I from 1 to n AI gi of x minus f of x plus 1/2 summation I from 1 to n bi gi of x minus f of x. By the triangle inequality, this L infinity norm is upper bounded by 1/2 the L infinity norm of this function plus 1/2 the L infinity norm of that function. But this is gamma, and this is also equal to gamma. The right hand side is gamma, exactly like the left hand side. Every term here is equal to gamma. This L infinity norm is equal to gamma. This means that if the A's and the B's are optimal coefficients in the sense of minimizing the L infinity norm of the residual, then also this set of coefficients is optimal. Because those coefficients are optimal, by the alternation theorem, we know that there are at least n plus 1 points, omega 1, omega 2 to omega n plus 1, such that the value of the residual using those coefficients is minus 1 to the power k, where k is an integer from 1 to n plus 1 gamma tilde, and gamma tilde is plus or minus gamma. So the residual evaluated at omega 1 is minus 1 to the k, that's minus gamma tilde. This can be either gamma or minus gamma. But then if you use omega 2, then you get the residual evaluated at omega 1 times minus 1, and so on. Like what we did here, let's take this and write it as these two terms. Here we are using the A coefficients, there we are using the B coefficients, and this summation is minus 1 to the k gamma tilde. Note that this is the residual if we use the A coefficients. This is between minus gamma and gamma. This bracket is also between minus gamma, and each bracket is multiplied by 1/2. The right-hand side is either gamma or minus gamma. How can the right-hand side be gamma? There is no way to get gamma on the right-hand side except when this bracket is gamma and this bracket is gamma. There is no way to get minus gamma on the right-hand side except when this bracket is minus gamma and this bracket is minus gamma. This means that the residual, whether we are using the A coefficients or the B coefficients, when evaluated at omega 1, omega 2, all the way to omega n, must also give us gamma or minus gamma. Subtract, we get summation I from 1 to n, ai minus pi, gi of omega k equal to 0. Let's write down this equation in a matrix vector form. We can have a vector with the differences here, a1 minus b1, all the way to an minus bn. On the right-hand side, we have the 0 vector of the n-dimensional space. And then here we have those g values. Note that this matrix here, its first row is g arrow of omega 1 transpose. The second row is g arrow of omega 2 transpose. And the last row is g arrow of omega n transpose. The g functions satisfy the Haar condition. This matrix here, which is the transpose of this matrix, must be invertible. And if it's invertible, then the only vector in the null space of this matrix is the all-zero vector. This means that b1 is equal to a1, b2 is equal to a2, and so on. The b coefficients are exactly the a coefficients. If the g functions satisfy the Haar condition, our solution to the L infinity minimization problem is unique.